The topic of my talk is related to the temporal growth of the entropy in three-dimensional turbulence. And as we all know, there have been many studies on the evolution of vortices, isolated vortices, pairs of vortices, and they all gave us very helpful insights in the dynamics of vorticity. But there has been done much less on the evolution of these structures in a turbulent flow. And the reason for that is very simple, because you have a problem to process this huge amount of data, because you not only have the spatial resolution, you also have to resolve the evolution with respect to time. And that's what I'm going to talk about here and now. And the figure which you can see here explains already or describes already a little bit the way of how we have done this. So what you see very nicely are these high vorticity structures, tube-like structures in a homogeneous isotropic flow. This is an isosurface plot at 10 times the mean square of the vorticity. And the way how we have studied the temporal evolution is done in these little subvolumes, which have about the side lengths of 16 Kolmogorov lengths. And they are nailed to Lagrangian tracers, which are moving through the flow. So this is our way to study the evolution of the vorticity field as a function of time. And that's the so-called quasi-Lagrangian frame, which we are using here. Before I start, let me just mention the collaborators on that problem. So on this particular question of the growth of entropy, this is Bruno Eckert and Charlie Döring. Very closely related to this topic is the question of the alignment between vorticity and strain. And this is something which we are currently investigating with Peter Hamlington, who is a PhD student of Werner Dahm, also at Michigan. And if I have some time at the very end, I'm going to briefly discuss some recent efforts which we have done to transform this whole machinery to a turbulent shear flow. And this is done with my colleagues in Ilmenau, Dmitry Krasnov and Thomas Böck. So before I dive into the numerical things, let me just set the stage. What is known on the growth of entropy in a fluid? And for those of you who attended the symposium in Nagoya 2 years ago, this looks very familiar, because Charlie Döring was by this time giving a talk on exactly this subject, which is summarized on this slide. And that was some of the main motivations which triggered us to study this in turbulence. So what you see here is the definitions of the kinetic energy and the entropy for some incompressible fluid in a volume V. The evolution is described by the Navier-Stokes equations. So you get this kinetic energy balance, and you get from the vorticity equation an entropy balance. And then by applying integration by parts and several inequalities, you're getting this relation. You are coming up with an inequality that sets an upper bound for the growth of the entropy in the volume V. And that goes at largest with the cubic power, as you can see. So the entropy cannot grow stronger than E cubed. And they went further, not just setting up these inequalities, they were also asking what kind of flows are producing these, or are there flows that can saturate these upper bound? And indeed there are. For sufficiently high values of the entropy, you actually see that there are flows which can saturate this bound. This is the growth rate, this is the entropy itself, and it goes with a third power. For smaller cases, it's a smaller growth, as you can see, with a numerical determined exponent of 1.78. And the structures which are causing these growth behavior are for the smaller exponent arrays of Burgers vortices, as you can see here, and in the strong growth rate case, these are basically colliding vortex rings. There is more known, and that's a very recent work which was put by John Gibbon on the archive, and he basically raised the question, how probable are these events, these potential blow-up events? Can we say something about this? Again, he started from the balance equation for the entropy. He defines local Reynolds and Grashof numbers, and then he can come up with an exact integral expression, which is given here. And then you can start to discuss the sign of this integrand, and the integral in total should be positive, but that doesn't mean that the integrand cannot be locally negative, and these are exactly the interesting events where this gradient, this spatial gradient, is larger than than the other two terms, and they have to be somehow overwhelmed by all these more or less ambient events. So this is not a rigorous result, but it suggests somehow that these events, if they are present, seem to be pretty rare. Well, there's more known, yes. And that's going back to the Kalman-Horvath equation, which is given here. And you know, you can exactly derive from this equation, again, the balance equation for the entropy. And as you can see, the exponent now is 3/2 instead of 3, as we had it for the inequality by Lu and Döring. This S is the skewness, derivative skewness, and we know that has a very weak trend with the Reynolds number. But nevertheless, we see that this 3/2 behavior is shown up here for this result. This is a result which is not holding for any incompressible flow. So we have to assume homogeneity and isotropy in order to get this. So it's a special case. So then the question immediately arises, can we build up a relation between both? And indeed we can. So we define capital omega as the square of the vorticity, and then we can basically rewrite the entropy and throwing away the volume dependence in our equation. So this is the equality by Lu and Döring. So we have already separated out the volume. So it comes here with the first power, it comes here with the third power, that makes in total the second power. And then we split up the cubic power in 3/2 and 3/2. We are using this relation, which holds for homogeneous turbulence. And then you basically can rewrite this inequality in something that has such a ratio of length scales in it, which are going with the 6th power. And again, reproducing the 3/2 behavior, which we have in the balance, which comes directly from the Kalman-Horvath equation. And then you see that there is this total length of the volume, which we are considering, and then there's the Kolmogorov length. So if you're going further down, if you go local in the flow, this factor becomes of the order of 1. And then you actually can make contact between both relations.
Can you explain the sign? Because in the upper one it's a plus, and the lower one it's a minus.
Well, this goes with a minus, the S. The S is negative, so it's positive. Okay, so that's exactly what we are trying to study in our simulations. So this is a picture, again, of these omega squared times the mean square, and you see this variety of structures, and you can expect that there are strong fluctuations local also in the growth, in the temporal growth of these structures. Let me say a little bit to these simulations. So we are studying homogeneous, isotropic, and forced three-dimensional turbulence. The resolution is 2048 cubed, and the Reynolds number for that resolution is pretty small, 107. So, but that was on purpose. We really wanted to resolve these very fine structures for other reasons, which basically have been discussed in these papers, which I have listed here. So Kmax eta times 10 means that we are about 8 times better than the usual resolution, which is applied for these direct numerical simulations. We are resolving the Kolmogorov scale with 3 grid lengths. And as you can imagine, these became pretty heavy simulations on a supercomputer, which is considered already as a dinosaur because it's 4 years old. But nevertheless, you do not have to go always to the biggest machines. Sometimes you can also do some nice stuff on somewhat older machines and just asking questions which go a little bit more into a sophisticated analysis. The computations took 45 days in total, so digesting all these data took, or is still going on, so it's basically a 2-year period over which we have been worked and are working on this amount of data that were generated there. If you want to study the evolution in time and you really put out at each time step the full velocity field, you would end up with something like 1,900 terabyte. Nobody is able to process these data, and that was the reason to go to these local co-moving frames. We have 100 tracers which are running through the flow, and each is attached with this little 51 cubed Eulerian grid, and is resolved in time, and that gives about 300 gigabyte. It's still a lot, but that's something one can handle. There's another reason to do this quasi-Lagrangian. What you're basically doing is you're removing the large-scale sweeping by big vortices, and when you are locally, it's exactly that effect which you are removing, and this can be seen here. So this is basically the distribution of the local velocity fluctuations, and this is the global Eulerian value which you would get if you are conducting the Eulerian analysis. So then the question might be, do we pick some interesting events? Because these tracers are running through the volume, and we are basically searching the needle in the haystack, as I will discuss later a little bit more detailed. And what you can see here is the PDF of the dissipation and the squared vorticity. For these low Reynolds numbers, you usually get that the tails deviate. When you go larger, as discussed in this paper, they approach each other, but that's not of interest for now. I just want to point your interest to these green arrows. And these are particular tracers, and we have just marked the global maxima of the dissipation, local at one point, and the squared vorticity inside these co-moving frames. So you see you can get pretty far out into the tails. So there is a certain probability that you're really picking some interesting events. Let me just make a little detour and say a little bit about the joint statistics of these two quantities. And so this is a fraction of this simulation, and here I plot the vorticity field, as I showed already before, together with the dissipation field. And as this distribution shows very nicely, both are strongly correlated, in particular for the very large amplitudes. So what you see here is the joint PDF, which is normalized by the single quantity PDFs, and that basically indicates that you here really have a strong correlation of these events. And this is very interesting and important, in particular when you want to discuss the vorticity strain alignment. And since we have these very well resolved data, we can actually apply some ideas which have been around already for a while, namely to understand why is the vorticity always aligned with the intermediate eigenvector of the rate of strain tensor. So what you're doing is you're basically decomposing the strain into a part which is due to the local vortex structure itself that causes a straining motion in the vicinity of the vortex core. And then there is the background strain, which is basically the straining motion which is coming from all the other tubes which are scattered around. And then you can apply this Biot-Savart type expression, which goes back to ideas from Koji Okitani more than 10 years ago. So we can directly evaluate this integral. We can calculate the background strain. And then you see this is the usual plot which everybody observes, the strong alignment with the intermediate eigenvector. And if you go to the background strain, you see that the alignment with the most extensional strain becomes visible. So there's a way of systematically sorting out these alignment properties. The next step, which we are currently working on, is also to study the time evolution of these events, because there's a certain persistence of the straining motion, and that's something which we certainly have to understand better. Let me now come back to our quasi-Lagrangian analysis. So this is a typical snapshot, time traces, of the entropy inside these little quasi-Lagrangian cubes. And these are all 100. So these are the time traces of all 100. I just have colored differently the ones that gave the highest amplitudes. And you see this is a pretty strong variation as a function of time. You can observe all kinds of features. So this is just for illustration. For this particular subvolume and this particular maximum, which is here, it's almost at the end of the simulation. It's just a single vortex tube which gets stretched and is passing this observation volume. Well, there has been some debate about whether the dissipation or the entropy comes first in those kind of high amplitude events. What we actually see is that it's both ways. So this is an example. So this figure is a blow up of that part, and you see dissipation comes first, entropy later. And this is another tracer Lagrangian track, and that's exactly the other way around if you're zooming into that region. So now let me come to the question which we actually wanted to study in this investigation, and that's what kind of growth do we see for the entropy in our local co-moving frames. And I have just sketched here the upper bound, which goes with the cubic power. And these are all the traces of these 100 individual subvolumes. And you can actually fit quite nicely, more or less, a 3/2 envelope to these events. And that's somehow interesting. It indicates that locally, not much different stuff is happening as the prediction of the von Karman-Horvath equation would give. We went even further down to study pointwise events. And the analysis which we did then is we conditioned the growth to the maximum, to a local maximum of this quantity. You see that we have here, for instance, very strong variations over such a longer time track. And when you are translating these two intervals, which are sketched here, these are two subsequent events in one of these cubes, that you get the following in this omega dot plane. So you see that there is something which grows very rapidly, in this case with a cubic power, but others do not grow that quickly. We can study how the structures look like which are associated with this event. So these are 6 snapshots of the squared vorticity. These are 2 nested isolevels. So this is 20 times mean square, and this is 10 times the mean square. And these are the corresponding isosurfaces for the dissipation field. And it's all in this maximum. And you see very nicely there are 2 filaments, 2 vortex filaments, which seem to attract each other. And while they are doing so, there's a strong shear layer which is forming in between, which is causing then the increase of the energy dissipation. So this was actually one event which got a very rapid growth in the entropy, and that was the one which got the biggest one. And when you're thinking now about our data, we had 100 of these cubes. We had 1,830 output steps, 51 cubed grids. That gives something like 2.4 times 10 to 10 data points. That corresponds basically with 3 full turbulent samples of that fluid. And you see that indeed these very strong events become very rare, or are very rare. In that sense, the ideas from John Gibbon are confirmed by our numerical studies. There are immediately questions: what can we do? What are the next steps? Well, it would be nice to have something like this for a higher Reynolds number. The Reynolds number was pretty small, as you might remember. And it's also not clear, this is something we also have to study closer, if this omega cubed growth, which we observed locally, is the end of the answer. It might not. There's, one can think of this regime when a Burgers vortex is stretched by a time-dependent strain field, and there's an additional dynamics of the Burgers vortex radius, and so that's actually an exponential growth which is suggested there. So it might be that we just have picked the cubic power of such a growth, which is then by some other dynamical reasons interrupted because we don't have a perfect configuration as we would have in such an analytical example. Before I summarize, let me just mention a little bit our recent attempts to a shear flow. So the first thing when you want to study this, you have to make sure that you are really resolving everything properly. And what we just did is we took the classical Kim-Moyne-Moser simulation for a channel flow, and we repeated that simulation at 4 times the resolution. So there's one at the usual resolution and one at 4 times the resolution. And this is the Reynolds shear stress profile. You see slight deviations here. And this is the mean, the plane average dissipation rate. It all looks OK, and nobody would really get excited about this. But if you want to study the statistics of the small-scale fields, then you should do a little bit more. Yes. As this picture suggests. So this is the PDF of the energy dissipation field. And now it's getting a little bit more tricky because you have to do the whole analysis as a function of height. So we have picked one plane in the viscous buffer layer at the beginning of the logarithmic layer, in the logarithmic layer, and in the midplane. And you see there is a certain behavior. This is the smaller resolution case. This is the higher resolution case. When you're just comparing these 2 plots, there is certainly a difference between both. And I'm afraid that we still haven't done a good job with this 4 times better resolution, as you can see here. So there's still some work to do. Why is it so important? Well, it's exactly about these structures which are sketched here. And if you want to study them, if you want to study their dynamic relevance, one should better resolve them properly. That's basically the main message which I want to bring over with respect to this issue. Okay, let me summarize my talk. We have seen that very intensive strain and vorticity events are not statistically independent. They are strongly correlated. We see that on a local scale, so we had, the scale was about the crossover scale between the inertial and viscous range. We can reproduce on a local scale this classical von Karman-Horvath result for the growth of the entropy, and the events which are causing very rapid growth are rare, and what we see in our particular example, this is strongly connected to interacting vortex tubes. So let me just thank a couple of people who make very useful suggestions on our way. I also want to mention the Jülich Supercomputer Center, which provided all this time within the DISA initiative. Otherwise, these computations would never have been possible. Thanks a lot.
You talk about in the region of strong entropy growth, cubic something. Could you write on the board what is cubic? Is that a function of time or something?
Yes, yes. It's a time derivative which is bounded so it's the time derivative which is bounded by the cubic power of the entropy. So it has dimensionally there is a viscosity cubed.
I'm trying to make some sense of this 3 to 10 to the 10 frequency ratio. Those events, how big are they? Because they're certainly not 1 point.
What do you mean, how big?
When you say you see 3 events, you are not seeing 3 points in which there are a strong blow-up. You're seeing 3 regions.
Yes, so what, well, this is inside these volumes, but what we have actually done then is a point-wise analysis. So we really went down.
How many points are there in this strong?
That's what you,
yes.
okay, let me
trying
just,
to
yeah.
make some zeros out.
So there are, yes.
There, okay.
Okay, so you see these other points which are scattered here around this. So these are actually the next neighbors which we have additionally monitored, so that you get a kind of idea, okay, how much is the variance of that. So that's what we did. Do you mean this?
Basically, do I see 3 events? Is that what we are seeing? 1 blue, 1 yellow, and
No. It's just, no. So this is, so think of this cube, which is moving through the volume. And the maximum is jumping from point to point while it evolves in time. That's why you get this kind of piecewise
that's okay,
behavior. So, and all the yellow stuff is this, and this corresponds with these points, and this interval corresponds with this behavior.
Okay, so how many of those events do you have?
Well, we had a couple of them, but this is the strongest one. It's actually just this one.
Yeah, sure. I mean, there's always one stronger one, but I mean, how many strong ones do you get?
Not that many. Maybe a handful or something. Yeah, not more. A handful.
4 out of 100.
Something
You
very
were
important.
following
Not 100.
cubes.
It's no. There have been. We have studied. That's.
No, I mean, I'm just trying to get a number for that.
So this is. That's why I actually.
So you're following
put this
100
side.
cubes. You're following 100 cubes.
Yes, we are following 100 cubes, and we have 6 cubes of these 100 where we get actually a rather strong entropy. That were these colored curves which
Okay, and then how long do they last in time steps?
this is about 10, 12 Kolmogorov times. It's pretty short.
Okay, no, I mean compared to those, I mean, you had 100 cubes, and then
Yes.
6 are blooming or whatever you call it,
Yes.
and each of them has 2,000 time steps.
No, the number of time steps is 18,300. We put out only every 10th time step because otherwise.
Okay, so I mean of those.
So this is the whole integration is
I know,
4
I
eddy
mean,
turnover
of that
times.
interval, how long is your bursting event?
The burst, I told you, 10 Kolmogorov times about.
But I mean, how much is that in output steps? I don't know how.
So we have the total integration time is about 4 eddy turnover times, and that's about 55, 60 Kolmogorov times.
So it's about 1/5 of that.
Yeah.
Okay, so you have out of those 500 pieces, 6 are bursting. So it's 1%.
Yeah,
1%
something,
of
yeah,
the-
yeah.
Okay, so that makes more sense.
Yeah,
It's
yeah.
3 to 10.
Okay.
I mean, which is a small number, I agree with that.
Yes,
So
it
it's
is.
like 1%.
Indeed.
You're saying that those very large events you see are associated with colliding vortices. I assume that there has to be some geometric properties that has to be verified in order for you to get the maximum growth rate. There's a literature of people looking at in experiments at colliding vortices. Have you tried to compare, or if these features are there or not?
The problem is inside these cubes, we only tracking segments of long cubes, of long tubes, right? This is one problem. We would have made, we would like to have a bigger observation volume, but that's basically not possible with these, with the given computational power we had. But we haven't, the particular colliding process we haven't studied that much. The first focus was just to see if the growth of the entropy, what is it doing in these local frames. As I said, the problem to my view is that we only get segments in these. So it's not clear if that's enough.
Yeah, just a quick question.
Yes.
Look at your omega cubic, the curve over there. What are you trying really to tell us? Are you saying that because this plot, we are going to approve the theory or demonstrate theory by the, as a Troy Dorings? Or because
No.
you pick a particular, let me make a comment. Your particular events are not really qualified, disqualified, because there are so many events going on.
Yes,
You pick a
yeah.
particular one. What kind of conclusion are we going to draw?
No,
Just
no.
want to.
No. Okay. The first question was, what do we see what the inequality and what the variational calculations provide? Do we see structures which can grow that rapidly? So the second question, and most of the analysis is statistical. I just talked at the very end about this particular event. Yeah, but the main result is actually not this particular event. The main result is actually this one. That's to my view the main, and then we were expecting to see some stronger growth. So since we didn't see it, we went more local to see if it is there. That's simply what we did. And I don't want to hang on this particular event. They are very rare, as we all know, and so that's what we see. And maybe if you go to a bigger Reynolds number, you see stronger growth. It blows even more, but that's something I cannot answer.